everyone. My name is Sanders Kleinfeld, and I'm excited to welcome Carlo Rovelli to Talks at Google today. Carlo is a theoretical physicist who directs the quantum gravity group at Centre de Physique Théorétique of Aix-Marseille Université. His contributions to the field of physics include more than 200 scientific articles, as well as 2 monographs on loop quantum theory. He's also the author of the best-selling popular science books, 7 Brief Lessons on Physics, Reality is Not What It Seems, and The Order of Time, which have been translated into more than 40 languages. He's here today to discuss his latest book, Helgoland, which explores the fundamental principles, challenges, and mysteries of quantum theory, tracing its genesis back to the revolutionary contributions of scientists including Niels Bohr, Wolfgang Pauli, Max Born, Erwin Schrödinger, and Werner Heisenberg, whose groundbreaking discoveries on the island of Helgoland helped kickstart the field of quantum mechanics. Thanks so much for joining us, Carlo.
Thank you very much, Sanders. It's a pleasure being here.
Great. So to kick things off, I have to confess, I've always found the field of quantum mechanics to be a little bit intimidating. So as I was reading the introduction to the book, it was really comforting to see you characterize it as difficult to understand. And I was wondering, for those of us like me who are fairly new to quantum mechanics, can you give us a primer of what the field is all about and why it can be so counterintuitive?
Sure. So the key point is that quantum mechanics is weird. It's incredibly weird. So the sense of unease that you are referring to is not just because it's advanced science, it's complicated. It's not just that. It's that it's weird for everybody, including for those who work into it. So let me say that in a couple of words what it is, what's good about it, and why it's weird. What it is possibly the greatest revolution in science ever, certainly one of the greatest. It started 100 years ago, 1925, so a century, so it's not something new, and has replaced the basis of mechanics, of classical mechanics. So it's really the core of modern science, modern physics, and it's as a basis of plenty of current technology. I mean, we're using a computer to communicate. Computers are made by little electronic circuits which are computed and designed using quantum mechanics, and works thanks to quantum phenomena, small quantum things. It's, lasers are a quantum effect, of course, nuclear power, nuclear bomb. Plus, it's used today for justifying the basis of chemistry, for understanding how the sun works, why it burns, to the formation of galaxies. So it's really the core of science, and it works fantastically. It works perfectly. In fact, one could say it's the best scientific theory we have had ever, because we don't have any single indication of where it goes wrong. It has always went right. Everything as predicted is correct. I mean, maybe it's not the final story, but we have no sense of where its limits. So that's a goodie. What's the problem? The problem is that you can use it. You can be an engineering, a chemist, somebody studying galaxies and use it. And a good student, I mean, students go to classes at university and take a course in quantum mechanics. You do the exercises, you predict, you go to the lab, you do a little experiment, it works out exactly as the theory predicts. But if you think about, if you stop and say, well, wait a moment, what am I doing exactly? The way the theory is formulated is completely weird, because the theory is formulated not telling you what happens, but only what you observe, what you see. So it's like you treat any system, whether it's a part of the sun or a little chip in your computer, you treat it as a closed box where you look at it and you see something, and then you look at it again and you see something else, and in between, it doesn't make sense to fit. If you try to fit what is in between, you start saying funny things. So it's like the way it's talked in books is that it is about observations. But what does nature know whether we are observing or not? I mean, is that about us? I mean, it's very confusing. And people came out all sorts of ideas to understand what is really going on. And in a century, we are really in a conceptual mess. We don't know what is telling us the best theory we have about the world.
Yeah. So you touched on this a minute ago. But you describe quantum mechanics as an interplay of three key principles: observations, probability, and granularity. I was wondering if you could elaborate a bit more on the significance of each of these concepts in the context of quantum theory, and how their synthesis allows us to model the behavior of particles.
Yeah, so two are easy, and the third one is complicated.
Cool.
The first you mentioned is a complicated one. So let me start from the easy ones. The easy ones are granularity, and that's pretty easy. I mean, that's just a discovery about nature. Things are granular at small scale. They literally are. For instance, light that comes from that lamp on my face, I give a description, as an electromagnetic wave that comes on me. I see a sort of continuous thing making me shining and lighting. But if we make a precise measurement, we see that it arrives on my face in little photons, grains, granular. So light really interact with me dot by dot. And in fact, if we tune down the light and have a screen, we actually see the dots one by one. And this granularity, it's all over. I mean, if you, for instance, the energy of the atoms, it's quantized, so that it's a quanta of energy, grains of energy, angular momentum for anything is just take discrete values instead of continuous values. So there seems to be a sort of bottom level where you go down to discreteness instead of continuity. I used to say that continuity is an approximation to many. Infinity is an approximation to many. Down there is always a final number, so to say. And that's the easy thing, number one. The easy thing, number two, is that it came as a surprise, but it came as a surprise just because we were used to Newtonian science. It was discovered with quantum mechanics that we cannot predict the future exactly, even if we have maximal information about something, right? So you're taught in physics classes before quantum mechanics, when you go to university, that in principle, if we knew the position and velocity of every particle universe, we could compute what happened next, which is sort of true because things are complicated. But, in principle, it's true that if you had, total precision on a classical, on a physical system, the old idea was the world is deterministic. So that determines the future evolution forever. Well, that's wrong. We have discovered as a fact that even if you measure something maximally that you can measure, you cannot say what's going to happen next. What you can say, it's a probability of different happenings. And that's right. Usually it's good enough because, first of all, when you have many things, probability just, average up and it becomes certainty. Averages evolve essentially in a certain way. But as soon as you go into small, you have this intrinsic probability, which is a de facto impossibility for us to predict the future. All right, so that's the second discovery. So the world is granular and is probabilistic, cannot predict the future. So far, so good. And then there's a third one, which is the hard one, and is the one that has given all the confusion. Well, technically it's called contextuality, and it's a fact that the theory is not about what happens, but is about what you observe. Even the language, when you open the books of quantum mechanics, is in terms of observables instead of variables. And the theory doesn't say, imagine you have a pen moving. The theory is not that in every moment the pen has a position, has a velocity, has an orientation. It doesn't talk about that. It talks you, if you look at it, it's here. Then you close your eyes, you look at it again, it tells you where it is. But if you try to reconstruct what happened in between, the theory doesn't say anything. It's not only that it doesn't say anything, but if you think about it, any possible reconstruction in between seems contradictory. And the prototypical example, Feynman said, that's all the mystery of quantum mechanics is this example. Imagine, as I said, you have something going from here to here. Imagine there's a wall in between with two holes. It's called the double slit experiment in quantum mechanics. It's always that. So there's a hole here and a hole here. So you see a pen in one point, you see a pen in the other point, and then you say, well, it has gone through one hole or the other hole. Now, it turns out that if you assume that it went through this hole, you get the wrong answer. If you assume it went to this hole, you get the wrong answer. So you have to assume, so to say, that it went through both. Namely, that when you look at it, it's a pen, but when you don't look at it, it's a sort of wave all over. And that's weird. That's the weird part of it. So discreteness, things are granular. Probability, we cannot predict the future. And observables. The theory, it's not about what happens, but what we observe. And the third one is a source of the mystery, which people have started in various directions to try to make sense of it.
Right. And that third one, I guess, is the one that is most famously presented in the Schrodinger's cat thought experiment that you talk about quite a bit in the book, and is also achieved a lot of prominence in popular culture. It's been in movies and television shows. And until I really read your book, I don't think I've fully grasped the implications of it. I was thinking about it as a very epistemological type thing where you don't know whether the cat is asleep or awake inside the box, but it's actually really a metaphysical statement. And I was wondering if you could talk through the experiment a bit more and discuss some of the significance of it.
Yeah, it's exactly like the two holes, right? So somehow, if you say, well, I see the particle here, I see the particle on the other side of the wall, and there are two holes. So I can make a computation and say where I should expect the particle, and I get it right if I do quantum mechanics. But then I say, well, imagine that at the middle of the time it went through one hole, okay? And then I get it wrong. And then I say, well, okay, maybe it went through the other hole, and I also get it wrong. And then I say, well, maybe it went half probability here, half probability here, I also get it wrong. So the only possibility is that when I'm not looking, I have to think that it is in both, right? And then people say, okay, fine. I mean, pens up in a wave and through hole and then converge. That's a solution, but that's not a solution, because if I look, if I look which hole goes through, if I look, I only see it here and see it there, or see it there, okay? And then what happens is that since I've seen it here, the result later is different. So this is actually done with particle with two holes in any laboratory. In many universities that do it for the students, and you actually see the mystery. But if you think instead of a particle going through holes, a cat having two possibility. So the old Schrödinger version was the cat was dead or alive, but it's not very nice. So if we think the cat could be asleep or awake, the theory forces you to say that it's neither awake nor asleep until you look. And then we're going to correct that, because I think that's a wrong take of the story. What it means exactly? It means that if you assume that at some point the cat is awake, then you can predict something, and it's wrong. If you assume that is asleep, you can predict things, and it's wrong. You really need two, both in some sense there, to make the right predictions. So the theory seems to say that when you don't look at things, they are in funny superpositions, that here and also here, the cat asleep and also awake. And that's not clear, because Sanders, if you were in a superposition, how would you feel, right? I mean, what does it mean?
Yeah. And I think that brings us to a key question that you ask in the book, where your observations are material in the science, and you ask, why does nature care whether we observe something or not? And exactly. I was curious if you could elaborate a bit on that.
Yeah, and this is somehow. Let me now shift to the general agreed sort of description of the weirdness of quantum mechanics to one particular way of trying to come out of this puzzle, and I mean, all the ways to come out of the puzzle are strange. So this is the one which I find less implausible. I mean, the other is worse. And it's a fascinating way. It's called the relational interpretation of quantum mechanics. I've worked on it. Other people have worked on it. Scientists have worked on it. Philosophers have worked on it. So the idea is the following, that this has nothing to do with observations. I mean, the observation is a wrong language here. The we observe, it's a wrong language here. The point, the mistake, it's confusing relations with observations, relationality with subjectivity. And to explain what I mean, think about another case in which we use the language of observation, but it's nothing to do with observation. In physics, in fact, when we talk about velocity. No, I mean, I think everybody who has taken elementary field physics class knows that velocity is relative to the observer.
Right.
So if you are on a train, you say, oh, this is velocity 0, it's not moving, meaning it's not moving with respect to train, but it's moving with respect to the Earth. So the velocity of something with respect to a train is different than the velocity with respect to the Earth, and it's different the velocity with respect to the Sun, and it's different from the velocity with respect to the galaxy, and so on and so forth. So it makes no sense to say, what is the velocity of the moon? Well, depending with respect to what, right? So velocity is a relational concept. It refers to two things, not to one. And we sometimes don't say with respect to what, because we give it for granted. I mean, usually we say, with respect to the Earth. We mean velocity with respect to the Earth. I mean, if you get a ticket speeding, it doesn't say it goes that speed with respect to the Earth, but that's what it means. And if a mother on the train says to the kid, stop, don't move, she doesn't mean jump out of the window or don't move with respect to the Earth. It means don't move with respect to the train. So,
yeah.
All right. So, but obviously, the relational aspect of velocity has nothing to do with subjectivity. There's not an observer here. The moon has a velocity with respect to the Earth and velocity with respect to the Sun, but not because the Sun observes the moon, has a brain, has a consciousness. It's nothing to do with observation, just relations. So I and others think that the correct way of thinking about quantum mechanics is that it tells us that all quantities are like velocity. So they're really relations, and not all physical variables are not characteristic of the object itself, are characteristic of, describe how the object interact with something else. So things have properties relative to something else with which it is interacting, and the property describes the interaction, not what happens to the object itself. So objects by themselves have no properties. They have properties relative to other things, and these properties mean the interaction. Now, if you take that perspective, you throw away the idea of observers, subjectivity. Nature doesn't care if we look not at things, but nature does care if two things interact or not. That's a fact of nature. So when the electron hits the screen, that's a fact, and that the electron has a position with respect to the screen. Okay. If the electron bumps against a wall, it has a position with respect to whatever it has bounced around. But the subtlety, and that's the way out of the tunnel, is that if something has the variable something has a value with respect to something, this has no influence of the value of that value with respect to something else. So the cat, in the story, the little Schrödinger story of the cat, there is a little poison or something that make the cat sleep that might or might not open inside in the box. So does it open or does it open or does not open? Well, with respect to the cat, obviously it's one of the two, not both, because it's an actual thing that happened with respect to the cat. But what happened with respect to the cat doesn't imply anything definitive with respect to me, until I interact with the cat. So the fact that the poison has got to the cat or not, it's a fact with respect to the cat, but this doesn't forbid the fact that if I want to compute something with respect to me, I have to consider both possibility until I do the calculation. And that's the way out. So the way out is relationality. That's why it's called relational interpretation. Think about reality not as a collection of things that have properties, but a collection of objects that interact with one another, and the properties come out in the interactions. So think relations rather than individual object with properties. It's a relational thinking, which is not new in a sense, but because we think relationally, plenty of things in our life a lot of things are relations in our light, are not entities. It's surprising that somehow all the way down to elementary physics is relations all the way down.
Yeah, it's a real key paradigm shift of quantum mechanics, a shift away from matter as the essence of reality. In the book, I think you expressed it really eloquently. You said there are no elementary entities that we can describe except in the context of their interaction with something else. This leaves us without a foothold, no place to stand. If matter with definite and univocal properties does not constitute the elementary substance of the world, and if the subject of our knowledge is a part of nature, what is the world's elementary substance? From where can we begin? What is fundamental? And I guess that's the question that I'd like to throw back at you. If we're only in a world of relations and relational phenomena, what is fundamental? I think we, as humans, we are looking for something really substantial to plant a flag on.
Do you want a sincere answer?
Yeah.
I think we make a mistake by aiming there. You said we as humans, aim at some basis, something fundamental on which, from which we derive everything else. If there was one, we would have found it already. Humankind. Let me just open up the topic a little bit. Humankind has been looking for the fundamental ground from which everything else derives since ever, with a long list of attempts, right? From God to matter to phenomenology, observations, hermeneutic circles, whatever information, energy. At some point, people say, "Oh, it's all energy; it's not matter." Philosophy, it's a constant attempt to find the principle from which everything else derives, and nobody has been able to convince everybody else about his own. Why? Because first of all, you can start from different points and reconstruct the world in different ways. The world admits to be reconstructed in different ways, but more importantly, the world is a complicated set of things which we can understand a lot about. We do, because science is incredibly powerful in connecting things, right? But physics is very good because it connects to everything. In the sense that we expect that everything satisfies physical laws, right? So the universality of physics remains very strong. But physics has tried repeatedly to find the basic ingredient. And, what is the basic ingredient in modern physics? In quantum field theory and general relativity and quantum gravity, it's very slippery.
Right.
Because the particles, the quarks, the electrons, they're not the basic ingredients. They're created, destroyed. They are quantum excitations of a field. They are this, granular thing that depend on the way you look at them. And quantum mechanics come like, a violent bomb there and shows that it doesn't work. We don't have a clear ground. But that does not mean that we don't have a good way of thinking about the world. We do have plenty of good ways of thinking about the world, which are coherent with one another. So let me say this. This is a pen, right? And there seems to be just plenty of properties of the pen itself. It's a pen, it's black, it's oriented in this way, in this position, this velocity. It's made by atoms, whatever you want. It's this color. Now, if we look at all these properties one by one, we start seeing that they're not in the pen. For instance, the fact of being a pen obviously is because we write with it. If somebody came from Andromeda and look at this thing, says, well, it's a thing, but it's not a pen, because a pen is something you write of. So it's the fact of being a pen depends on our use of it. It's black, but that's a color. The color depends on our vision. Animals see things with different colors. So the color is really something that pertains to the way my eyes work, the light works, bounces on the thing. All right, so it's a single piece. Well, it's not true. I can take it apart. It's made by atoms. Each one has its own position and velocity. Well, it's not true, because quantum mechanics tell us that the atoms' position and velocity depend on the interaction with me. Does this take away the reality of the pen? No. The pen is very real, but it's a combination of all these relational relations we have with everything else. And if you think for a moment, suppose it didn't have any relation with everything else. I couldn't see it, I couldn't touch it, I couldn't do anything with it, or nobody else. So what would it mean to be real? It's a strange, reality is a strange notion. We can play around. So I think that the shift you said is a major shift, because we tend to say, okay, whatever reality is a set of things with properties. The shift from that to reality is a set of interactions, and the objects are the nodes of this interaction. A pen is a node of all these possible interactions. It's not dramatic in our everyday thinking, because we think in terms of interactions, but it's dramatic in our foundation of thinking. And I think it's a step ahead. It's not a step back.
Right. Fundamentally, everything is relational. And as you were also alluding to earlier, there's a probabilistic element to it as well. And I was interested if you could elaborate a little bit more on that as well. It's sort of the quintessential question that Einstein posed: Does God play dice? Or, as you rephrased it in your book, are the laws of nature really not deterministic? And in the book, you say, 100 years after Heisenberg's and Schrodinger's bickering on this, the question is still open. So I'm wondering what the implications are in your mind in terms of the deterministic nature of everything that we experience in the world.
Yeah, absolutely. It's true that we're still bickering about it. I have colleagues, in fact, that do not like this relational reading of quantum theory. And one of the reasons for which they don't like it is because they're very attached of the idea that the world is deterministic. So, I mean, whatever happened today determines what happened tomorrow. And in fact, there are other attempts to make sense of quantum theory, but careful. Let me be precise here. I keep thinking about these things, because in these other ways, you assume that behind the scenes, so to say, there is something else which is going on, which is really deterministic. But for one way or the other, we have no access to this, or we cannot predict it.
Right.
Let me just make it concrete, because there are two alternative interpretations of quantum mechanics, which are the most popular ones, besides relational one. One is the hidden variables. And as the name of the interpretation implies, there are some variables which are hidden. Okay, so something happens that it's in principle impossible to access to, which determines what's going to happen tomorrow. But it doesn't change the fact that we cannot predict the future, right? Precisely because this variable are hidden, it remains the fact that we cannot. So, as I can say, if you have something you don't know tomorrow, you can always imagine that there is something today that determines it, and you don't have access to it. You can add to your set of beliefs of what exists that the information of tomorrow is already there today. But what do we get? And the other popular interpretation of quantum mechanics, which has also got out in the popular press, people have written books about it, it's a so-called many-world interpretation, in which the cat is really awake and also asleep. When you look at it, you see only one, because you yourself split in two. And so there's one version of you that sees the cat awake, and one version sees the cat asleep. So nothing is probabilistic here, because there are two of you. But it is probabilistic, the fact that you don't know which one you're going to be tomorrow, right? Because I look at the cat, I see it awake, and I say, okay, of the two, there's my brother who has sinned, but I didn't know before which one I'm going to be. So I cannot make prediction, because I don't know in which sense I can make it. So again, I have to be probability. So it doesn't really matter. That's where I'm going. Whether nature is probabilistic or not with respect to God, who sees everything, assuming that God exists. In a sense, even if the world was completely probabilistic, you'll say, okay, well, God sees the future, so it's already determined. So the question is not so deep after all. I mean, there will just things happen, and it's a fact that it's impossible to predict what's going to happen tomorrow. given maximal available information today. So I think that at the end of the day, the unpredictability which has been discovered in fundamental physics, it's just a fact we have to confront. And there's nothing wrong with it, right? I mean, it's humankind has lived for millennia thinking that the future is unpredictable. I don't know why we should be attached to the idea that there's absolute determinism or predictivity.
It's true. I think perhaps maybe we just want to be able to predict the future, and that's all there is there.
Oh yeah, we would like so much to know
nice.
what happens tomorrow. Of course, maybe that's all there is. Yeah, right.
Right. So I think any discussion of quantum mechanics would be incomplete if we didn't at least touch on the concept of entanglement, which you describe as a phenomenon by which two distant objects maintain a kind of weird connection, as if they continued to speak to each other from afar. So you describe this scenario in which there are two entangled photons, one that's sent to Vienna and one that's sent to Beijing, each of which could be like the color red or the color blue, but when observed, they always turn out to be the same color. So this is very, very counterintuitive, certainly for me, and I think for a lot of other people. How does this work, these connected particles that could be separated by vast distances?
It is counterintuitive, and it's very subtle when you go into details. And in fact, it's a subtle phenomenon. I even hesitated putting a chapter in the book about that because to get it right exactly what happens, it's subtle. But then, as you see, it's really the sort of a quintessential quantum phenomenon, this strange connectiveness. Is no sense in which you get a sort of sudden transfer of information from one to the other. So it's not that one of the two is blue, decides to be blue, and tell the other, "Hey, I'm blue. You too. You have to be too." That's not what happens. It's we're pretty sure about that. Neither. What happens is that there was a previous agreement, so they knew to be both blue before, and there were good reasons for exclude that one as well. So it's something far more subtle, and what is far more subtle is that let me put it this way: to check that they're both blue, you should be in both places instantaneously, and nobody's in both places instantaneously. So what do we mean when we say that there is an instantaneous transfer of information? Nobody can check that. So what is the sense of that? What we really mean is that whatever happened there, if we bring the information up and then later in time you compare them, at the moment in which anybody can make this comparison, it sees that they're both the same.
Right.
But since phenomena are relative to an observer, it's only in the moment in which the comparison is made that this has happened. Before, it's like the cat, which is both alive and asleep and awake. So with respect to Beijing, something happened. With respect to Vienna, something happened. With respect to whoever gets all information and compares, something happened. But with respect to each, there is a coherent story where information never jumps. It's only when you bring pieces together and try to juxtapose it that you get this apparent instantaneous transfer of information, which is not real, because you're not allowed to bring these pieces. Reality is really relational in this sense. Then this relationality, you don't see it macroscopically because it's in the minimal thing. You have to do super subtle experiment to bring it up. But the world with respect to me and the world with respect to you cannot be made exactly coincides. There are little discrepancies. There's a perspectival aspect that forbids a coherence down to the Planck constant scale.
Mm-hmm. Yeah, so you refer to it as basically a dance for three, I believe, where you have one particle, the other particle, and then the observer, and we're all participating in this together. So
exactly, and that's the way we're putting it. Entanglement is a dance for three, not for two, because whoever compares is the third perspective, and the third perspective is the one that compares and is the one that doesn't see the long distance information jump.
Right, right. So earlier in the talk and also in your book, you touched really briefly on some of the applications of quantum mechanics that have already begun to transform technology and society. And you mentioned, lasers, semiconductors, and the physics of formation of galaxies. I was wondering, if you look 10 to 20 years down the road, are there any other groundbreaking advances you can potentially foresee scientists making as a result of all the research into quantum theory that you're doing?
People are working on quantum computers today. There's a
Mm-hmm.
huge investment in quantum computers. You can exploit this quantum weirdness to make computers sort of immensely faster than the current computers with
Right.
obvious applications. The theory of quantum computers is absolutely solid, and so it's perfectly possible to do them. The technology, it's hard because an object that becomes quantum is an isolated object. As soon as you start to interact with too many things, its quantum weirdness disappears. Okay, sort of it's diluted out in the interaction, and you don't see it. And that's why the actual a cat is a big thing. The interference between the quantum interference between the two cats, it's a very delicate phenomenon. You don't see it because the cat is too big. So you can always assume, oh, the cat was asleep. Oh, the cat was awake. So big things tend to hide quantum behavior, and that's why making a quantum computer is hard, because you have to isolate it. So I don't know if this is technology. I'm a theoretician, so you have to ask the people doing technology if it's actually doable as people hope, or it is more hard than one expect. But certainly would change a lot. I'm sure there are other applications of quantum mechanics we haven't seen yet. They're going to come up. It takes long to general relativity. It's older than quantum mechanics. 100 years old. We have
Right.
a GPS that works thanks to general relativity. Nobody would have ever imagined at Einstein time that you're going to use general relativity, to find your ways downtown Manhattan, to find where is the 27th Street.
Yeah, so we'll just have to stay tuned, I guess, and see what can be developed on top of quantum mechanics.
That's right.
Great. So we have a bunch of great questions from the audience, so we're going to pull them up now. And we have a question from Timur here. Are the results of the double slit experiment the same when the observer is not a human? For example, a trained animal, a robot, camera, etc.
Yeah, I'm very happy of this question, because in a sense, this is a key question. And the answer is a resounding yes. A strong yes. I mean, there is absolutely no evidence that there is anything special with humans when things happen. You can try do any quantum experience, interference or entanglement or anything else, and replace you looking human with a robot, and the result is absolutely the same. And that's what strongly indicates that there are some people who say, oh, the quantum mechanics really happen when consciousness sees something, but consciousness has nothing to do with that.
Great. Jay-Z is wondering, to build on Timur's question, do the results depend on the expectation of what the results might be? For example, if expecting the results to be A or B, do you get a different result versus if expecting A, B, or C? Do our expectations matter?
No, they don't. Certainly they don't. What matters, let me, don't get it wrong. So listen to the full thing. What matters is what we look at. Okay? So if we look at one thing or if we look at another thing, the result is it's contradictory, sort of, in one sense. So, but not because we look at one thing or the other things, because the kind of interaction that we have in one case and the kind of interaction that you have in the other case probe the system differently. So, and the system manifests itself in interactions. So whether it's an interaction of one kind or interaction of the other kind, brings up different properties of the system, and this might be contradictory to one another. Namely, sort of one interaction sort of cancel the information about the other interaction. And this was completely clear in the early days of quantum mechanics, when Bohr and Heisenberg and company were discussing on that. But they were thinking in terms, I observe this and I observe that, right? I use this machine to to interact with the quantum system, or this machine interact with the quantum system. And nothing to do with a machine, with the apparatus. It's just the kind of interaction, the kind of Hamiltonian interaction term that is in play that determines which quantities are realized in an interaction. So nothing human, nothing depending on what we expect or anything which is mental. Everything is down there physical, who is interacting with whom, and properties are in the interaction, not in the things.
Another question. David is wondering, this relationality seems similar to the fact that we can't interact with anything outside of our light cone in relativity or the inside of a black hole in general. Do you view this the same way?
Yeah, there is a quite analogy, even if there are differences, because the theories are different and the details are different. But there's a strong analogy. In fact, even more, because let me put it this way: relativity, Einstein relativity, it's a discovery that we will make a mistake when we thought that we assumed that simultaneity is absolute. Okay, the two things happening in distant places, we can say which one happened first or they happen at the same time. So there was a wrong assumption. And in fact, the remarkable thing is that Einstein understood that. That's what Einstein understood in a formalism that was already there, because it had been developed by Lorentz, by Poincaré, by mathematical physicists before him. So he understood what it meant. And with quantum mechanics is similar, because we have this formalism that works to describe nature, and we didn't understand what it means. And relational quantum mechanics is the idea, yeah, we understand what it meant. It meant that we're making a mistake. Like in relativity, we make a mistake of thinking there is absolute simultaneity. Here, we're making a mistake in thinking that there is an absolute reality of the properties independent of the interactions. So simultaneity is relative to a state of motion with respect to which you define it. The values in quantum mechanics are relative to the kind of interaction which are there. And in both cases, in fact, the analogy is strong, because in both cases, we usually we use a language of observers. You know, relativity is relative to the observer, and quantum interaction are relative to the observer, quantum measurement related to observer, as if it was something subjective. But there's nothing to do with subjectivity. It's relativity in both cases.
Question from Krish. If all particles are the result of fundamental interactions, does it also apply to the fundamental point particles described by the standard model too?
Yes, very much so. In fact, I don't know if Krish is a physicist or not, but the popularization version of the standard model is that yeah, there are a certain number of particles and they bounce against one another, and that's the world. But you know, if you take a class in quantum field theory, try to understand the quantum model for real, that's not so simple, not at all, because these particles are actually quantum excitations of a field. So the particles are not down there. The particle is what happened when the field interacts with you. So much so that when we compute, in particle accelerator, you throw two particles in, and then you see what comes out, and you compute it before. In the computation, you're actually summing the different Feynman diagrams, which are different stories of what happened in between. So to compute the probability of some outcome, you consider all possible outcomes and you sum all of them. So that's exactly Schrödinger cat. You're saying the two particles come in and this happened, but also this happened, but also this happened. So it's like the Schrödinger cat is alive, but is also asleep, and is also this, and is also this, and also this, or the particle through the two holes. It passes by here, but also here, also here. So explicitly, in quantum field theory, if you look at it, the way we do calculations, it's not true at all that the world is made by particles that bounce. The world is made by particles that are particle only when they interact with me, or with an apparatus, or with something else. In between, they open up in a cloud of possibility, exactly as I was saying before. So yes, the particles of the standard model are not entities. Let me be precise. I mean, Google is full of smart people. So let me put it. In fact, I'm giving this answer to you, try to be much more sharp and precise than usual. When I talk to the general public, assuming that you don't know quantum mechanics, but still, particles are not entities in current standard model quantum field theory. Particles are modes of interactions of the field. It's how the field interact with something else, my machine, my detector at CERN that measures something.
Another question, Sangamitra is wondering, does an interaction change the state of what's being interacted with? So is there any way to actually know the true nature, state, attributes of anything in the quantum world?
The answer to the first question is yes. And in fact, it was Heisenberg himself, which is the true person who opened the quantum mechanics door first, who a few years later noticed it. So in quantum mechanics, when you interact with something, you're always affected somewhere. And for a while, it was hoped, in fact, he hoped that was it. That was the only thing we have discovered. The only thing I've discovered is that there's no way to affect something, to measure something without changing it a little bit. But that's not sufficient for understanding quantum mechanics. The subsequent discussion clarified this is true. You cannot delicately look and not affect the system, except in some particular situation in which you can. But that's not sufficient to explain the mysteries of quantum mechanics. Now, for the second part of the question, again, I think that the right direction to think here is not, all right, so we affect what is there, so we don't know what is there. I mean, forget what we don't know. We are not describing an unknowable world. If we try to fill up, we get strange nonsense stories which are useless, in my opinion, and misleading. We should describe the phenomena. And the phenomena is what happened in interaction, not what happened before or after. And that's the key message. Talk in terms of relations, not what is... And if I may, just a small parenthesis, to enlarge a little bit the discussion, we think in terms of relations all the time, right? People who do software, they're not dealing with entities, they're doing with relations. People who do psychology, they're not doing with entities, they're doing with relations. People who do economy, they're not really doing with entities so far away. They do with relations between economical actors. If you think of your family structure, that's relational, it's not entities. We use relational notions all over. And when I talk about the pen, I clarify that so many things we consider in the things are really relational. So I think the message is that if quantum mechanics can be thought effectively in this way, we can look at our general way of looking at the world and ask, let's get away with this obstination of willing to find entities behind any phenomenon.
Question from Bo on the many worlds hypothesis. If we observe the cat asleep, wave function has collapsed. Is this because we'll exist in the reality with this outcome versus a separate parallel one where the cat is observed awake?
So let me distinguish. In the many world, there's no collapse of the wave function. So the wave function never collapses. The wave function has two components, one with the cat asleep, one with the cat not asleep. I look at the cat and my wave function splits in two. So now there are two Carlos, one that sees the cat asleep, one sees the cat sleeping, and so on. So this means that there are not two copies of me, but plenty of copies of me that see the world in all possible ways. This is coherent. It's not incoherent. I have intelligent friends that think this is reasonable, but I don't think this is useful. It's multiplying copies of all of us in a way that I feel doesn't help. From the relational perspective, there's no wave function. There's nothing to collapse because there's no wave function. Wave function is just our calculations, like the prediction of the weather. You look at the thermometer and you change your prediction about the weather, but it's not because the weather changes. You get some more information and your prediction jumps. What is real, or what we will call real in the relational interpretation, is just the actual seeing the cat alive or asleep or not, or some interference fact of the cat. So again, there's no collapse of the wave function in the world. There is a collapse in your calculations just before you adjourn your data, because now you want to compute something else whose probabilities change because something has happened.
Next question from Joao. Thanks for the talk. How do you suggest combating the idea that quantum mechanics needs no interpretation, and those who are against the study of the foundations of physics?
Good. So there are two arguments for quantum mechanics needs no interpretation. One is good and one is bad. So one is good is that, well, I don't care. I use quantum mechanics and it works. And that's a very good argument, because if an engineering is studying quantum computers, say, I don't care about the interpretation. I know exactly what my computer is going to spit out the probability distribution of the varied outcome, and I don't want to know what happened inside. He's right. He doesn't need to think too much about that. But science is not only about applications. Science is about understanding better and going ahead. I do quantum gravity. I want to apply quantum mechanics to general relativity, and I need to understand quantum mechanics better to understand how to apply to general relativity. The objection, the second argument is, the different interpretations cannot be empirically distinguished. At present, relational quantum mechanics, many worlds, hidden variables, you cannot make an experiment and distinguish. So what do we talk about? And here's my answer to that. Is the Earth the center of the universe or not? That was a huge debate in the Renaissance, all the way from Copernicus to Galileo, Newton. You might say, of course, it's a scientific debate. Not only is it a scientific debate, it was extraordinarily fruitful scientific debate, because changing our views of the whether or not the Earth is the center of the universe completely changed our way of thinking about motion, about velocity, about the solar system. We rearranged things. Instead of Earth, planets, we had sun, planets, satellites. So it's completely rearranging of that. This rearranging was needed to go to do Newtonian physics, to do physics. But if you think for a moment, the Earth being the center of the universe is a testable hypothesis. Can we measure it, whether the Earth is the center of the universe or not? No, of course we cannot, right? There's no measure that tell us that is the center. In fact, many people at the time, including the people who condemned Galileo, by the way, were saying, what are we talking about? The distinction between the Copernican system, when the Earth spins and goes around the sun, and the old Ptolemaic system with the Earth in the middle, cannot be solved empirically. And they were right. It cannot be solved empirically, because you can always rearrange this from the point of view of the Earth. Just everything becomes already more complicated. You don't go any insights. So science is not just about things which are distinguishable empirically. Of course, science need to check theories distinguished empirically, but the actual discussion is how about to think the world? What is the best perspective to think the world? And the Copernican revolution, the Copernican perspective obviously was better. History clarified that completely. We would not have had Galileo, Huygens, Kepler, Newton, and modern science without the Copernican revolution. So it's a similar discussion, I believe. It is a philosophical discussion, it's a conceptual discussion, but it's a scientific discussion. There's one perspective that I think will take us ahead in the future. And I've my own views on that. Others have different views, but the actual discussion is very productive and it's core of a scientific debate. So if a scientist want to ignore it, fine. I mean, it's just do something. We don't have all to do the same thing. But if the argument is this is not a scientific discussion, that's definitely a wrong argument, in my opinion.
Next question from Doug. Were you surprised to find echoes of these ideas in Buddhist philosopher Nagarjuna's writings? Have his ideas changed or influenced your thinking about quantum mechanics? I guess someone's read the book, so...
Somebody read the book. Yeah, the book. In fact, we've been talking about my book. The book is a lot about quantum mechanics. It's not just this part that we discussed, sort of the key ideas. It's also about a description about the historical origin. So Heisenberg discovered the theory in the island, and Schrödinger discovering the theory while making love with his secret girlfriend and all that. But then there's a long part of the book in which I discuss the sort of more general philosophical implication of this relational perspective. And one chapter I have Lenin and Lenin philosopher, the head of the Soviet Union, and his philosophical text, discussing with a great Russian intellectual, which is Alexander Bogdanov, issues which are exactly parallel to the discussion about quantum mechanics. And then I have a chapter of the book of Nagarjuna, which is a monk, a Buddhist monk of many centuries ago, 2nd century in India, which is a super classic of Indian philosophy. It's like, Aristotle and Plato for Western philosophy. It did not influence me in thinking about quantum mechanics originally. I discovered it very late, and I discovered it because people kept telling me, I mean, this relational perspective that you're defending, it resonates a lot with the perspective of Nagarjuna. So I read it, and I was extraordinarily taken by this. Not the mystical aspect of this. This is not a mystical reading of the book of Nagarjuna. It's a logician, Nagarjuna, and it's a metaphysician. It has a way of describing reality in terms of relations. Exactly. So in a sense, it offers a rather solid philosophical perspective in terms of which the relational interpretation, you can think at the relational interpretation. You don't have to think of relational interpretation in terms of Nagarjuna thinking, but it has strong arguments, for instance, counter objection like, oh, you cannot have a relation without having entity with properties to start with. Nagarjuna is very clear in saying that's wrong. In fact, it's the opposite. If you have a relation, necessarily the idea, you cannot build relations out of entities with properties. There is something primary in the relations. So it did help me clarifying things and discard some wrong idea. I took something out of it, definitely, but it was not influential. It's actually coming out in me and my colleagues' ideas of relational interpretation of quantum mechanics. And obviously, Nagarjuna knew nothing about quantum mechanics.
Great. So we have time for, I think, one more question.
Oh, time flies.
Yeah. Question from Brian. How do you view time and a series of instantaneous observations within the framework of relationships? That's the last question. It would require a long discussion. I could give you my perspective, but it would take time. So let me say something else. Quantum mechanics was born in 1925. Not in 1926 when Schrödinger wrote the Schrödinger equation, the year before. And in fact, Heisenberg got the Nobel Prize for the invention of quantum mechanics for a spectacular paper in which he just got the right idea of observables and non-commutativity. But then that was very, very, very confused. It's Max Born with his collaborators who actually put up the theory. So the full quantum mechanics is in 2 or 3 papers written by Max Born and his collaborator and Heisenberg in parallel Dirac in 1925. And what Max Born had in mind, and I think he was on the right track about space and time, is that we should, when we think about quantum phenomena, it's wrong to sort of presuppose a continuous space, positions, and time, and put into this space the particles and try to localize everything. It's the other way around. We should think of quantum mechanics as a set of interactions, I would say today, observations, a set of facts which are discrete. And the temporal and spatial reality
comes up from the large number of little facts happening. So it's a discreteness that builds up the continuity of space and time. Because we have large scale with respect to the Planck constant. That was Max Born's perspective, and I think that's the right way of viewing that. So we should start from the realization of variables and interactions in standard quantum mechanics, the outcome of the measurements in the language of the books, and not put space and time before that. We should put space and time after that, and that becomes a bit confused in saying like that, but becomes very, very clear in quantum gravity. Because in quantum gravity, that's exactly the case. There's just no space-time continuous. Space-time continuous is built by the quantum phenomena.
Well, on that note, we are out of time. So I want to thank you again, Carlo, for joining us at Talks at Google. And everyone, please check out Carlo's new book, Helgoland, now available. So thank you again very much, Carlo.
Sander, thank you very much. This was great, and thank you for the question, and also for the great question of the public. Very, very sharp and good. I enjoyed it a lot.
Great, thank you.